All right, let's run through the construction of continuous time Markov chains. Quick side note, they are often called Markov jump processes, but they are one and the same. So we're kind of going to have to do a rehash of the previous clip, but we're going to write things down more mathematically so one can then go ahead and solve problems. So the first feature of continuous time Markov chains are their paths, which are mathematically going to have to be step functions. So step functions are functions that are constant on given intervals. So in other words, you're given, let's say, a partition of time, or it doesn't have to be time in general, but in our case it is. This partition, these time points or timestamps, generate intervals. So here's an interval from S1 to S2, and they're half open for a reason we'll discuss. In other words, if we look at the half interval for S1 to S2, the point S2 is not actually in the interval. S1 is, but S2 is not. So now the value of the function, on this half open interval S1 to S2 is just the value at the start. It's actually the value anywhere inside, but in here it's fs1, and so on and so forth. So in general, we can look at kind of any one of the quote unquote steps, right? They look like steps, and that's exactly what's being defined here. So at any little time t, t is going to look at what interval is being indicated by the indicator. So if A here is S1 and B is S2, then the value is again fs1, and the indicator is going to put a 1 and a 0 otherwise. Yeah, so in other words, if here is my time, if my time t is right here, then the indicator is going to throw up a 1, and I'm going to land into this part of the if statement, and the value is going to be whatever value there was at the beginning of the interval. And if my t is not there, then it's going to be 0. So each step is kind of constructed separately, and then all you do to construct the function at any time t is you just sum up over all of the intervals. And we'll look at this in detail in a little bit, I think in maybe a couple of more slides. The half-open nature of the intervals has to do with these filled in or open circles, right? So here, the open circle is saying, look, the function is not, doesn't have any value here. It's actually taking the value at time S2 up here, not down here. So that's a point of discontinuity where the value is always on the right-hand side of the interval. And this is kind of, if you think about sort of a stochastic process flowing in time, this is a much more natural way to do it than if the filled-in circles were half open, because then if you think of kind of time moving forward, you want to all of a sudden be in some new state where as opposed to if the right-hand side of the circle is filled in, then it's sort of unclear when that moment, right, that jump to the next state actually begins. So the half-open intervals are important, and they construct kind of a reasonable flow of time for the process. So the next thing to kind of write down are the what are called the arrival times or jump times of the process. They're essentially times at which the continuous time chain is going to switch states. So I'll call them here arrival times. You can call them jump times, changes of state, whatever it is. So each tk is going to be marking the time at which x changes state for the kth time. So easy enough. So in the example here, we have a bunch of states. I wrote down x, y, z, but it's actually uv also. So z, uv, x, y are all states. And t0 is kind of canonically always going to be defined at 0. So this time is not random. The other ones will be. xt0 is going to first begin at state x, just like in the picture. xt1 is the first time at which we jump to state 1. That's going to take the value y right there. xt2, it looks like we jump to state z. xt3, let's see, we jump to state v. Okay, I got that correct. xt4 is jumping to state u right here, and xt5 is going back down to the state y, and then so on, and so forth. And so, these states are really going to be prescribed, as we'll see, by the embedded chain, which is a discrete chain. So let's keep going for now. So we have these arrival times or jump times, and I'm going to do the same thing as I did in the definition of the step function, which is to define a step. So here I've taken the time a little t, right? So this little time little t is deterministic, and it's going to have to fall in some, one of these half-open intervals. In here it just happens to fall in the interval between t1 and t2. The time between the first change of state and the second change of state, and when it does so, the value there is going to be prescribed by xtk. So in this example, xtk, so k is going to be a 1 in this example, the one right here, and the value xtk is equal to little y. But in general, if we're going to ask what is the value of xt, well, we're going to sum up over all of these steps. And if you think about it, really, for t is deterministic. So in other words, this sum is only going to hit one of those intervals. There's no way to hit several of them. Time t falls in exactly one of those intervals. So this sum, even though it looks complicated and very large, in the end it boils down to just one indicator and one value. And the reason we use the sum is just to write down, to avoid writing this if statement. And so it's just a matter of kind of notation, but hopefully you see what's going on here. We have these steps. Any little deterministic time little t that we want to know the value of the process at is going to pick out exactly one step. So if we sum up overall, it gives us that precise value that we want. Now, the next thing we know is that we're going to have to stay at each time, at each state, for an exponential length of time. So here, this is an exponential variable. This is an exponential random variable. The lengths are, the steps, I mean. And so we know that every single state is going to keep a rate. So state z keeps a rate rz. So that's a non-negative number, which is synonymous with the word rate. And when x enters the state, it's going to have to wait there for some time tau z, which we know is exponential, with that rate. So the one little caveat is kind of has to do with the fact that we stay, every time we visit state z, we're going to have to stay there for an exponential period of time that's independent of what was done in the past. And so what we're going to do is we're going to generate IID copies of tau z. And of course, it doesn't have to be state z in particular. We could do this for state x, for y, for v, for u, it's, for all of them. We're going to generate these IID copies. And now, if on the kth change of state, xtk is equal to z, which just happens to enter state z, then this is the amount of time that we wait. So tau k z. And you can notice that if k was 3, that's going to be independent had we on change of state 6 or on jump number 6. If we visit z again, we're going to stay there again for an exponential length of time. The exponential is going to have rate z, but it's going to be independent of the previous state. So in this diagram, maybe y is a better illustrator. What this is saying is that this time, which is exponential with rate ry, is going to be independent of this state here, which begins at the 5th jump time. Those are independent, but both exponential and identically distributed, right? Exponential and both distributed with the rate ry. However, this guy is distributed with rate rz. This one is distributed with rate rv, so on and so forth. Okay, now, how do we know where to move next? This is what's called the embedded chain. So we're going to have to actually use a discrete time Markov chain to let us know where to go. The exponentials are going to be saying how long we stay in a state. The embedded chain is what's going to tell us where we go next. This is, by the way, one reason why we don't have self loops. We're going to stay, and we're never going to stay here again. In other words, you're never going to have a scenario where you wait for an exponential length of time at some state in here x, and then all of a sudden transition back to state x and then wait here again. That's not going to happen. So here's why it doesn't happen. There is this notion of the embedded chain. It is a discrete time Markov chain. I'm going to call it Z in most examples. So every single continuous time Markov chain X has an embedded discrete time chain, Z. And this is the thing that's going to tell it where to go. It's going to tell us where it goes up, down, to this state, to that state, and so on. And we're going to make one little caveat. It can be any discrete time Markov chain with one little catch, which is that the self-transition probabilities are only allowed to have self loops in the case when the rate is 0. Here, and so now we have to kind of think, what does the rate 0 mean? Well, an exponential with rate 0 means that the time is infinite, meaning you wait in the state forever. And if you wait in the state forever, in that case, it makes sense to kind of close this embedded chain off with a self loop. In other words, let's just keep everything in that state. We know exactly what happens from now on, which is nothing. We just stay in state x. However, when the rate is not 0, it means that we're going to leave the state eventually, and in that case, the embedded chain better have no self transition, right? So the probabilities, the one-step transition probabilities for the embedded chain, which I'm calling here BXYs, these one-step transition probabilities are sort of just what you would expect from a discrete Markov chain, with this one change that you can have no self-loops, and anytime you put in a self-loop, your associated rate for that state better be 0, which indicates we stay in that state forever. And that's what I wrote here. Rx 0 implies that the holding time is infinite. Holding time is another a name for waiting time. And yeah, we can kind of look at this right here. What does an exponential variable satisfy? Its survival time is e to the minus rate times time. Well, this is basically saying if the rate is 0, this, no matter what the time is, we're going to evaluate this at 1. So this is saying that we're always going to stay, right? The waiting time is always greater than any deterministic number t, and therefore, the wait time is infinite. So this is the final kind of sort of summary of this clip, which is just giving a little bit more rigor to the previous one. We already know all this, but here we're writing it down in mathematics. Any continuous time Markov chain X will have two ingredients. The first thing is a state space with a bunch of rates. These are non-negative numbers. And the next component is an embedded chain, which tells us where to go. Every time we leave a state, we have to know where to go. That's what the embedded chain is for. And that embedded chain has this feature that it'll have no self-transition unless for that particular state, the rate is 0, which indicates the process is over, it's staying in that state, and it's staying there for an infinite amount of time.